Thanks for the introduction. I would like to present our paper entitled Two-Stage Resampling for Bidirectional Path Tracing with Multiple Light Subpaths. Recent advances in bidirectional path tracing reveal that the use of multiple light subpaths can improve the efficiency of BPT, namely the reduced noise as shown in this slide. The left image is rendered by using conventional BPT that samples an I subpath and a single light subpath and connects each vertex of I and light subpaths. The right image is rendered by using BPT with multiple light subpaths. As shown in this slide, BPT using multiple light subpaths can reduce the relative mean square error. Resampled Importance Sampling BPT, RISBPT for short, proposed by Nabata and colleagues, first samples multiple light subpaths, then a single light subpath is resampled to generate a full light path, by considering the contribution of connections between each vertex of I subpath and pre-sampled light subpaths. Therefore, the computational cost for the resampling process is proportional to the number of pre-sampled light subpaths. Using a small number of pre-sampled light subpaths is fast, but it leads to the correlation of the light subpaths, resulting in high-intensity noise as shown in these images. On the other hand, using a large number of pre-sampled light subpaths can alleviate the path correlation, but it also increases the computation time for the resampling process, making the possible iteration count smaller, resulting in noise. We propose a two-stage resampling BPT to address these problems. In equal time rendering, our method can handle a 2 or 3 orders of magnitude larger number of pre-sampled light subpaths than RISBPT. As shown in equal time rendering comparisons, RISBPT is susceptible to light subpaths with an extremely high contribution due to a small number of light subpaths. This affects the entire image since the pre-sampled light subpaths are shared by all the I subpaths, which can be found in the whiteboard in the left image rendered by using RISBPT. On the other hand, since our method uses 10,000 light subpaths, our method can alleviate such artifacts. RISBPT that uses a smaller number of pre-sampled light subpaths induces unstable noise reduction as shown in the convergence plots. Our two-stage resampling BPT can provide stable and better noise reduction than RISBPT as shown in these convergence plots. Our method can reduce the noise up to 2.3 times than the state-of-the-art method. Since our method can handle a large number of pre-sampled light subpaths efficiently, our method can alleviate these high-intensity artifacts due to path correlation as shown in this slide. Now I would like to review the previous work. Probabilistic connections for BPT, PCBPT, provides important sampled connections between the vertices of subpaths to generate full light paths with large contributions. PCBPT prepares multiple light subpaths shared by all the I subpaths and then resamples a small number of connections through importance sampling. Then the connected full light paths are weighted by using multiple importance sampling, MIS. Unfortunately, the MIS weighting functions used in PCBPT remain unaware of the change in the path probability caused by resampling, resulting in less efficiency as shown in the insets. Nabata et al. Built upon PCBPT and proposed a resampling-aware weighting function for BPT using multiple light subpaths. Although this MIS weighting function can handle the change in probability due to resampling and can be more effective when a large number of light subpaths are used, this method shares the same problem as PCBPT in that the number of pre-sampled light subpaths is limited to several hundred due to the overhead. Next, I would like to describe the basic idea of our method. Since our method builds upon RISBPT, we briefly explain the resampling process of RISBPT. RISBPT first generates M light subpaths and K cache points in the scene. To sample a full light path, an I subpath is first generated, and the nearest cache point of the I subpath vertex is searched. For each cache point, the probability mass function, PMF, is constructed and used to resample a light subpath for the nearest I subpath vertex. RISBPT renders an image by iterating these processes. The computational cost to construct PMFs at all cache points in the scene is proportional to the product of the number of the cache points, k, and that of the light subpaths, m. The construction of PMF involves costly evaluations of visibilities between the cache points and the light subpath vertices, and evaluations of BSDFs at the light subpath vertices. Therefore, if we want to increase the number of light subpaths, m, without increasing the computational cost, we opt to reduce the number of cache points, k, and to reduce the cost to construct PMF itself. To handle a large number of light subpaths, we propose a two-stage resampling method for BPT. In the first resampling stage, we sample a large number of light subpaths, M1. To increase the number of light subpaths, M1, without increasing the computational cost, we construct the PMF only once in the scene, resulting in reducing the computational cost from order km1 to order m1. In addition, we evaluate a cheap PMF without the visibilities and BSDFs. In the first resampling stage, m light subpaths are resampled from m1 light subpaths. The second resampling stage is almost identical to the resampling process of RISBPT. The only difference between our second resampling stage and RISBPT is that our method uses different subsets of light subpaths at cache points, while RISBPT uses the same set of light subpaths at cache points. The use of different subsets of light subpaths at cache points can alleviate the path correlation. Now I would like to explain the algorithm of our two-stage resampling. In the first resampling stage, we construct the PMF P1 using the following equation, where Fy is the energy of the light subpath y bar, P is the path density of the light subpath y bar, and G is the geometry term between the cache point C and the light subpath vertex y. As shown in this equation, the computational cost of P1 is proportional to the number of light subpaths, M1, as shown in the denominator. In addition, the PMF P1 depends on the cache point C due to the geometry term G. The geometry term G prevents us from constructing the PMF globally, thus we aim at deleting the geometry term G from the PMF P1. To delete the geometry term G from the PMF P1, we cluster the light subpath vertices into a binary light tree, as shown in this slide. For each cache point, we select M clusters so that the geometry terms between the cache point and the light subpath vertices in each cluster are nearly constant. In this cache point, these clusters are selected so that the geometry terms in each cluster are nearly constant. To sample M light subpaths from M1 light subpaths, one light subpath is resampled from the light subpaths in each cluster. Then the PMF P1 to resample a light subpath from each cluster is expressed by the following equation, where capital C represents the cluster. Since the geometry terms in the cluster C can be considered as constant, the geometry terms in the numerator and the denominator are cancelled out, resulting in the PMF independent of the cache point C. Since the PMF P1 becomes independent of the cache point and depends only on the light subpath y bar, our method can construct the PMF only once. The second resampling stage is almost identical to the resampling process used in RISBPT. The subtle but important difference between RISBPT and our second resampling stage is that the two-stage resampling can use different subsets of light subpaths at cache points, while RISBPT uses the same set of light subpaths at all cache points. This mitigates the path correlation as described before. This slide shows the equal iteration count comparison between RISBPT and our two-stage resampling approach. To validate our two-stage resampling approach that uses cheap PMF ignoring the visibility between each cache point and each light subpath vertex and the BSDF at each light subpath vertex, we compare it with RISBPT using a similar number of light subpaths as shown in the slide. After 16 iterations two-stage resampling, the left image yields similar results as RISBPT, the center image, though cheap PMF is used for light subpaths in the first resampling stage. Since our method reduces the computational cost of the PM4 two-stage resampling takes only 21 seconds while RISBPT takes 2 minutes for an equal iteration count. This slide shows an equal time comparison between our two-stage resampling approach and RISBPT. In the equal time rendering of 2-minor two-stage resampling approach can iterate 96 times while the iteration count for RISBPT is only 16. In this experiment the two-stage resampling approach can reduce the error 2.4 times than RISBPT as shown in the insets that visualize the absolute percentage errors. Now I would like to show some results. We first measured the mean absolute percentage error, MAPE, and the number of iterations of the Sponza scene with 10 minutes rendering for sparsely sampled values of the number of light subpaths in the first resampling stage, M1 equals 1000, 10,000, 100,000, and that in the second resampling stage M equals 100, 500, 1000 as shown in this slide. In this experiment, M1 equals 10,000 and M equals 100 or 500 yield small values of the MAPEs, and M equals 1000 leads to larger errors and a smaller number of iterations since the computational cost of the resampling PMF is high. As shown in the right graphs, the iteration count in equal time rendering, i.e., the computational time per iteration, depends largely on the number of light subpaths in the second resampling stage, not on that in the first resampling stage. We found that M1 equals 10,000 light subpaths in the first resampling stage and M equals 200 light subpaths used in the second resampling stage work fine and are used in all the examples. This slide shows equal time comparisons between BPT, PCBPT, RISBPT, and our method. The rightmost graph shows the convergence plots of each method. As shown in the insets and the convergence plots, our method outperforms BPT, PCBPT, and RISBPT. The numbers under each image indicate the mean absolute percentage error and relative mean square error. The bold fonts indicate the best performance, namely the smallest errors. The Sponza scene is illuminated by an environment map, where the illumination enters from a small region at the top of the building. The inner wall beyond the arches is illuminated by indirect illumination, and it is difficult to sample such light paths due to the occlusions. RISBPT yields better results than BPT and PCBPT. However, the right arch in RISBPT is slightly brighter than the reference and noise can be seen on the wall beyond the arch. Since our method uses a large number of light subpaths and different subsets of pre-sampled light subpaths at cache points, it can sample light paths with non-zero contributions for such difficult cases. The classroom scene is illuminated by area light sources located on the ceiling and an environment map. In this scene, RISBPT can considerably reduce noise compared with BPT and PCBPT. However, the artifacts can still be seen in RISBPT. The wall of the hallway and the whiteboard in RISBPT are brighter than the reference. Our method can mitigate such artifacts and can reduce noise further. The bedroom scene is illuminated by an environment map, where the illumination enters from a small gap in the curtain. As shown in the convergence plots of RISBPT, the noise reduction in RISBPT is unstable, though it eventually converges. This unstable noise reduction is problematic for progressive rendering, while our method reduces noise steadily. The house scene is illuminated by area light sources inside the house and an environment map. The house scene is rendered by each BPT method combined with vertex connection and merging. In this scene, the bottom inset of RISBPT is slightly brighter than the reference, but that of our method is much more similar to the reference image. Let me conclude my presentation. We have proposed a two-stage resampling for bidirectional path tracing. Compared to the previous BPT methods with multiple light subpaths, our method can handle 2 orders of magnitude larger number of light subpaths. Thanks to the use of a large number of light subpaths, our method is stable and has better noise reduction.